So welcome to Focus Private Tuition. So we're going to wrap up our August online lessons with this topic, solubility product. So let's talk about what it is. So solubility is the extent to which a solid dissolves in solution. The extent to which a solid dissolves in solution. Okay. So when we add ionic solids to water, you need to know that they are going to be hydrated. So the ions in the ionic solid are going to be hydrated. And the degree of solubility here depends on the type of solid, but also on the temperature and pressure. So we're going to look at hydration later on, but you need to understand that when ionic solids are added to water, they're going to be hydrated. So they're going to exist in solution as hydrated ions. Okay, let's proceed. So there will come a point where the water can no longer hold any solid, and this point is called saturation. Any additional solid is not going to dissolve. So as you continue to add your solid to the water, it will become saturated, and at this point you cannot dissolve any more solid. Any additional solid after this point is not going to dissolve. You need to understand that. So the maximum amount of solid that will dissolve in a solvent is called solubility. The maximum amount of solid that will dissolve in a solvent is called solubility. So solubility has the units grams per cubic decimeter, and like we said before here, it's temperature dependent. So you see figures quoted with specific temperatures. Solubility is usually given in grams per cubic decimeter. However, it's also possible to show your solubility in moles per cubic decimeter, whereby you simply divide the grams per cubic decimeter with your MR for the specific solid. So let's look at an example. The solubility of barium sulfate at 298 K is 0.0025 grams per cubic decimeter. You can give this solubility in what? In moles per cubic decimeter. And all you simply have to do here is calculate the molar mass of your barium sulfate, which is 33.4 grams per mole in this case. Therefore, the solubility, you're going to dissolve your 0.0025 grams per cubic decimeter with the MR, and you're going to get this figure here, 1.07 times 10 to the power -5, now in moles per cubic decimeter. So just know that, like we said here, it is simply the maximum amount of solid that will dissolve. The maximum amount of solid that will dissolve, we call it solubility. So at the end of the day, you can see here that its units are similar to concentration. So people tend to confuse this with concentration. The units are similar here, but when we're talking about dissolving ionic solids, just know that we'll be talking about solubility. The maximum amount is referred to as solubility. Okay. So in a saturated solution, we have this amount here. We have the concentration of barium 2+ ions. Remember, I said that when we add these ionic solids to water, they're going to be hydrated. So we're going to have the ions, the hydrated ions, barium 2+, being equal to the sulfate ions here, 2-. This is because for this solid here, when we dissolve, for every mole of the solid that we dissolve, in the case of barium sulfate, we produce 1 mole of barium 2+ ions, and we also produce 1 mole of sulfate ions. The concentration in our solution, and they're going to be equal to the solubility at saturation here, which is 1.07 times 10 to the power -5. So you need to understand what's happening here. Let's talk about something called solubility product. We need to understand that an equilibrium is established between dissolved ions and undissolved solid when a sparingly soluble solid is dissolved in a solution. So an equilibrium is established between dissolved ions, those that are hydrated and in solution, and your undissolved solid when a sparingly soluble solid is added to a solution. So just understand that there is an equilibrium which is set up there between the undissolved solid and the dissolved ions that are already in solution. So if we have a sparingly soluble solid AB there, dissolved in a saturated to dissolved to saturation, the following equilibrium is established. So your A and B ions are going to be hydrated. So A, B plus AQ and BA minus AQ. Here I hope you understand where the B plus and the A minus are coming from. Here the ratios at which these two are going to combine. So remember, this one represents the charge that was at with this ion B, and this B here represents the charge of A. So this is why we have a B plus with A here, and then A minus with our B here. At the same time, we also have the molar ratios A and B here. So this is just a generic equation. Okay, so you need to understand that an equilibrium is established here between the undissolved solid and the dissolved ions there in solution. Okay, so when we apply the equilibrium constant Kc to show, remember what you did for Kc earlier on, where Kc is equal to the concentration of your products here over reactants, but here, since this one is a solid, we do not include it, which we said it in our earlier videos. You can go and check this out. So you do not include the solid, so your Kc ends up looking like this. Okay, so there's a new constant here that we're talking about here that's called the solubility product. So which is a result of applying the equilibrium law here. So Ksp is the equilibrium constant for a sparingly soluble product in a saturated solution. It has the same formula as Kc. So remember that it has the same formula as Kc, but we name it Ksp, solubility product. So Ksp here in this case is going to, for this generic equation, is going to be given by this. So if your hydrated ions A, B plus here raised to the power of A, this is the stoichiometric ratio as we saw here, and times the concentration of B to the power of A minus here raised the concentration raised to the power of B. So it is the product of these concentrations that are in solution. This way we call it the solubility product. The product of the concentration of A and the concentration of B here is what gives us our Ksp. And remember, we do not include solids, so we're just going to be left with these two. Okay, and take note here that Ksp is a fixed value for a specific solution and temperature. So this is temperature dependent. And okay, so let's proceed. So Ksp should always include state symbols in the expression. This is important. Okay, using the barium sulfate as an example here, this is how you're going to write an expression in terms of our Ba2 plus and our sulfate ions, concentrations and solubility of barium sulfate. So you're going to say your Ksp is going to be equal to the concentration of barium 2 plus ions times the concentration of your sulfate ions. Remember, said for every mole of barium sulfate will form one mole of this and one mole of this. So you see this is going to be raised to the power of 1 and here to the power of 1. So that's your expression, and you can manipulate here the fact that you're going to have one more of this and one more of this per every mole of the barium sulfate. Therefore you can write Ksp in terms of just the solubility of barium sulfate. So it's going to be the solubility of barium sulfate squared. The solubility of barium sulfate squared, because here we're saying the ratio, every time we have a mole of barium sulfate, we're going to form 1 mole of this and 1 mole of this. So this is similar to just saying the solubility Ksp is equal to the solubility of the barium squared. Okay, so let's proceed so you can do those mathematical manipulations there if you understand your ratios. So just like for Kc, we need to work out the units, and these vary according to the reaction. So if you work out the, okay, let's look at an example here. Work out the units for this Bi2S3 solid. So your Ksp is going to be what? Your Bi3 plus raised to the power of 2, and your sulfur here 2 minus raised to the power of 3, because these are the ratios here. Okay, so your Ksp will look like this. Ksp is going to be equal to the concentration of this raised to the power of 2, because here will form 2 moles of Bi every time this solid dissolves, and will form 3 moles of our sulfur every time this solid dissolves. So you raise to that stoichiometric ratio, and so that's your expression for Ksp for this solid. And for the units, you need to calculate your units as follows here. Your moles per cubic decimeter squared, because remember this is concentration, times your moles per cubic decimeter to the power of 3, and this is going to be equal to your moles to the power of -3 bracket 5 here. And if you know your laws of indices, the product law here, you're going to multiply that, so that's going to be moles to the power of 5 and negative dm raised to the power of -15. Okay, so you need to be able to calculate your concentration, your units for Ksp like that. So Ksp can also be calculated using the solubility of value. So we can give you the solubility of value and ask you to calculate Ksp. So let's look at that. Calculate the solubility product of lithium carbonate here when its solubility is 13.3 grams per cubic decimeter at 20 degrees Celsius. Okay, so the first thing is to you're being asked to calculate solubility product. So write an expression for Ksp for this specific solid. So lithium carbonate is going to dissolve to give you 2 moles of lithium plus, because that's its ratio here, and 1 mole of your carbonate ions like that. Therefore its Ksp is going to be the concentration of lithium raised to the power of 2 and the concentration of carbonate ions raised to the power of 1. So now that we have an expression for our Ksp, we can go on to calculate the solubility of lithium carbonate in moles per cubic decimeter. So here it's given in grams per cubic decimeter, so you just have to divide by the MR of your lithium carbonate. So therefore this is going to be equal to 13.3 divided by 74, or MR, and the solubility now in moles per cubic decimeter is 0.180. Okay, now that we have our solubility in moles per cubic decimeter, we can go on to figure out the concentrations of the ions. So we know that when 1 mole of lithium carbonate dissociates or dissolves, it's going to produce 2 moles of lithium, because that's its stoichiometric ratio here in the formula, and 1 mole of carbonate ion. So at equilibrium, what do we have? The concentration of lithium is going to be 2 times the concentration of our lithium carbonate, which is equal to 0.36 moles per cubic decimeter, and our carbonate, its concentration is just going to be equal to this, which is 0.180, because it's 1:1 with the original solid here. So it's going to be 0.180 moles per cubic decimeter. Now that we have those concentrations, we have to substitute into our expression for Ksp. 0.36 now raised to the power of 2, remember these powers, and our 0.180 raised to the power of 1, giving us a Ksp of 0.023. So you must be able to figure out the equilibrium concentrations first, and so write an expression here, figure out the solubility. So you must be able to figure out your solubility and relate this to the concentrations of the hydrated ions, and finally substitute into your Ksp. So you must practice to do this Okay, let's proceed here. Now, lastly, the units are also important, like we said before. So your units are moles per cubic decimeter here, squared, because for this is for the lithium. You have a square here, times your moles per cubic decimeter for the carbonate here, and you apply your product rule here, which is -3/3. So this 3 is going to affect your moles here. So moles to the power of 3, -3/3, -9 for the GM for the decimeters there. So that's it. Let's look at something called the common ion effect. So what is the common ion effect? The common ion effect is where you add an ion to a saturated solution that is the same as one of the ions already present. So when you add something to a saturated solution and this happens to contain an ion which is already present in solution, then you're going to experience the common ion effect. So what happens? What is it exactly? Let's look at an example where we add sodium chloride to water and you form a saturated solution. So when we do that, the reaction is in equilibrium. The reaction is going to look like this, so you're going to have your sodium chloride here forming these hydrated ions, right? Na plus Aq, Cl minus Aq. So when we have a saturated solution and we add more of chlorine ions, for example, to this system here, you're going to come in and add more of the chlorine. What's going to happen? So you need to remember Le-Chatelain's principle. So according to Le-Chatelain's principle, the equilibrium will shift to the left to use up your excess chlorine ions, and we observe a precipitate of sodium chloride being formed, and as a consequence there will be lower concentration of the sodium ions. So this will cause your equilibrium to shift to this side, forming more of the sodium chloride, and in the process we're going to have less and less of the sodium ions. So in other words, your solid becomes less soluble because it's now moving in this direction to form this solid. So it's going to become less soluble when you add a common ion to a saturated solution. So this is the overall effect of adding a common ion. Okay, so it will be the same even if you added sodium ions to this. It would still move to your left in order to remove the excess sodium ions. Okay, right, so we are not going to cover this in this series, partition coefficients. So if you'd like to proceed with up to the end of this topic, you can always contact me so that we proceed with our online lessons. However, for this particular series we are done. We're going to end at this particular concept, but as always, you can contact me so that we talk about partition coefficients. We will cover this in our next series of online lessons. So I'll see you next time. Enjoy your studies.